what if empty space isn't actually empty? Like, what if the vacuum between the stars and, I mean, literally between the atoms in your own body is actually a rigid infinite grid holding the physical universe together?
It's a huge question.
Yeah, so today we are taking a deep dive into a 2025 paper by independent researcher George James Dukas. And our mission is to investigate a single, seemingly random number spat out by a particle collider. A number that, well, according to Dukas, is the direct mathematical signature, proving that the void of space is actually a highly structured mathematical architecture.
Right, and it is a premise that challenges the very bedrock of modern physics.
Yeah.
Because we have spent nearly a century treating the vacuum of space as a featureless void, like a blank stage where the actors, particles and forces perform.
Right.
But the proposition in this paper, which is transdimensional unified field theory, or TDUFT, it argues that the stage itself is the main character and the particles are just vibrations of its floorboards.
Okay, let's unpack this, because the setup feels like something out of a hard sci-fi novel, but it is grounded in real physical data.
Yeah.
The story starts at the relativistic heavy ion collider, known as the RHIC, at Brookhaven National Laboratory. And what they do there is, frankly, incredibly violent.
Oh, yeah.
They accelerate protons to a significant fraction of the speed of light and smash them into each other.
The word violent is entirely appropriate. The kinetic energy involved in these collisions is so extreme that it momentarily mimics the thermal conditions of the very early universe, mere fractions of a second after the Big Bang.
Wow.
Yeah. So when you concentrate that much energy into a subatomic volume, you literally boil the quantum vacuum. You force the underlying reality to reveal its mechanics.
And when they boil that vacuum, particles pop out.
Yeah.
Specifically, the RHIC experiment was looking at these particles called hyperons. So listeners, if you are picturing a standard proton or neutron, those are made of up and down quarks. But when things get this energetic, the vacuum starts producing heavier, more unstable components like the strange quark. And a hyperon is a particle that contains at least one strange quark.
Precisely. And in this specific run, the researchers were looking at pairs of hyperons, specifically the lambda particle and its antimatter counterpart, the anti-lambda.
Okay.
These are generated simultaneously as a pair directly from the energy of the collision. They are promoted from being virtual fluctuations in the quantum vacuum into real observable particles.
And we actually have a visualization from the source material that paints this perfectly. So listeners, imagine two spheres floating side by side. One is labeled with the Greek letter lambda. The other is an anti-lambda, which just has a little bar over the letter. And pointing straight up from the top of both of these spheres are parallel blue arrows.
And those arrows represent what we call their spin alignment. Now, in quantum mechanics, spin doesn't mean the particle is physically rotating like a top, but rather it has intrinsic angular momentum. It has a built-in magnetic orientation.
Okay.
And the experiment showed that when these lambda and anti-lambda pairs are born close together, their spins are highly correlated. They tend to align in the same direction.
And here is the conundrum that kicks off Dukas' entire paper. The RHIC didn't just notice that the arrows were pointing in the same direction. They measured the exact numerical degree of that short-range spin correlation.
Right.
The number they got was exactly 0.388, and they measured this with a 4.4 sigma significance, which in particle physics means there is less than a 1 in 100,000 chance that this is a fluke or statistical noise.
It's a hard physical reality.
Yeah.
Which presents standard physics with a massive headache. Because standard quantum chromodynamics, or QCD, which is the reigning theory for how quarks behave, absolutely expects there to be some correlation.
Because the physics demand that the spins influence each other, right?
Exactly. But standard QCD cannot derive that exact numerical value of 0.388 from first principles.
Wait. If QCD is our best model for the strong nuclear force, why can't it predict the number?
Because at the energy scales where these hyperons are forming, the mathematics of standard QCD become notoriously difficult to solve. They become nonlinear and chaotic. To get any usable numbers out of standard physics here, theorists have to bolt on extra model assumptions.
Oh, I see.
Yeah, they have to plug in fitted parameters based on previous experiments just to make the equations function. They can't start with a blank sheet of paper, write down the laws of physics, and arrive at 0.388.
So standard physics is essentially looking at the data after the fact and adjusting their models to match it.
Yes.
But Dukacho's paper claims to have the exact mathematical recipe derived entirely from first principles with no artificial tweaking.
That is the claim. But to get that recipe, Dukas-Sturr's transdimensional unified field theory demands that we abandon the Standard Model's conception of a smooth, featureless quantum vacuum. We have to embrace the idea that the vacuum possesses an intrinsic physical geometry.
So, what does empty space look like according to TDUFT?
According to this framework, the vacuum is an infinite structured geometric grid called a V-lattice. And the entire architecture of this lattice, the spacing, the tension, the way it folds into higher dimensions, is governed by the golden ratio.
Okay, the golden ratio field. I think most people with a passing interest in science or art know roughly what that is. It's approximately 1.618. We hear about it in the proportions of the Parthenon or the spiral of galaxies,
Right.
but applying it to the structural foundation of the quantum vacuum feels like a massive leap. Why would the foundational building block of the universe be based on a geometric ratio?
Well, what's fascinating here is that within TDUFT, the golden ratio isn't just, an aesthetic curiosity. It is a mathematical necessity for dimensional scaling.
Okay.
Because if you are building a universe that operates consistently across multiple scales, from the microscopic quantum realm to macroscopic gravity, you need a geometry that is perfectly self-similar.
Like a fractal.
Exactly like a fractal. The golden ratio, which mathematically is exactly 1 plus the square root of 5 all divided by 2, is the only irrational number that has a perfectly continuous fractal property in its algebra.
So it is the ultimate architectural blueprint for a self-sustaining structure. If you zoom in on a fractal, the pattern repeats infinitely. TDUFT is saying the universe is built on a lattice that scales perfectly because of this ratio.
Furthermore, TDUFT introduces an operator to deal with time and spatial contraction on this lattice. This operator is the mathematical conjugate of phi, represented by the Greek letter Ci.
Let's lay out the math for that, because this is where the paper's core argument starts to crystallize. If phi is 1 plus the square root of 5 divided by 2, its conjugate to psi is 1 minus the square root of 5 divided by 2, which gives us a negative number, approximately negative 0.618034.
Now, in quantum field theory, when you want to calculate the probability or the physical density of a state, you square the amplitude. The paper does this with the conjugate.
So you are squaring negative 0.618034.
Yes. If you square this conjugate to find what the paper calls the second-order vacuum density operator for this infinite lattice, you get a positive number. Specifically, an endless algebraic decimal 0.38196601125, and it goes on infinitely.
Wow.
And this pure mathematical number, 0.381966, is claimed by TDUFT to be the universal baseline density of the vacuum. It is the geometric constant that sets magnetic permeability entropy density, and crucially for our RHIC experiment, the short-range torsion coupling.
Okay, this is where we have to pause and look at the numbers side by side. The pure mathematical density of this theoretical golden ratio vacuum is 0.381966. But the physical skin correlation measured at the particle collider, the real-world alignment of the lambda particles was 0.38. That is incredibly close.
It is tantalizingly close.
But wait, in the world of high-energy particle physics, close doesn't cut it. It's off by about 1.6%. If a theorist walks into Brookhaven and says, my theory predicts your data to within 1.6%, the experimentalists are going to throw them out of the room.
Oh, they absolutely would.
A 1.6% gap is a massive chasm. It usually means your theory is fundamentally flawed. If TDUFT is the perfect blueprint of the universe, where does that 1.6% missing correlation come from?
That gap isn't a flaw in the theory, it is actually the crux of the paper's predictive power. The difference between those two numbers represents the transition from the pure math of the lattice to the messy reality of physical existence.
Let's look at the exact difference, because the paper lays this out clearly. The RHIC measured 0.388000000. The pure lattice math gives us 0.38196601197. If you subtract the pure math from the physical measurement, the gap is exactly 0.0060339887.
To understand where that 0.006 comes from, we have to revisit how these particles were created. The Kerr density number 0.381966 represents the baseline state of a virtual pair on the lattice. It is the mathematical ideal of the vacuum when undisturbed. But the RHIC didn't measure virtual particles floating undisturbed in the void.
Right, they smash protons together at the speed of light, they drag these particles out of the math and force them into physical reality.
Exactly. And in TDUFT, whenever a virtual particle transitions into a real observable particle, it hits what is known as a continuum limit. Moving from the discrete geometry of the quantum lattice into the continuous space of physical observation triggers a requirement. The paper describes this as a convergent infinite harmonic attenuation series.
Okay, convergent infinite harmonic attenuation series. That is a massive wall of jargon. How does that actually work mechanically?
Think of it like plucking a guitar string. In a perfect theoretical vacuum, that string vibrates with pure, flawless mathematical precision. But if you submerge that guitar in a pool of water and pluck the string, the water resists. The physical environment dampens and broadens the vibration.
Oh, that makes sense.
In TDUFT, the water is the reality of the macroscopic universe, and the attenuation series is the mathematics showing exactly how that pure vibration is dampened and modified when it crosses the threshold into reality.
So translating that pure virtual state into a real physical state requires an energy exchange. The paper calls this leading residual term the entropy remainder. And when you run the attenuation math, that entropy remainder comes out to exactly that finite gap we just discussed, 0.0060339887.
This raises an incredibly elegant equation. The observed spin correlation in the real world is simply the pure vacuum density, the conjugate squared, plus the entropy remainder, 0.381966 plus 0.006034 equals the experimentally observed 0.388.
Here's where it gets really interesting for me. It's the pure lattice math is the wholesale price of a particle. But bringing that particle out of the vacuum and into the real world, you have to pay a finite entropy tax or a transaction fee of 0.006 to the universe to cross that border.
That analogy captures the mechanics perfectly. And we must emphasize that this entropy tax isn't just a convenient fudge factor that the author reverse-engineered to fix his equation. Dukas argues that this specific transition correction is inherently built into the core framework of TDUFT.
Right, the author states very clearly that nothing new was invented for this specific paper. He didn't just add a random plus sign at the end of the equation to make it match the RHIC data. The framework already existed. But to prove that this isn't just mathematical sleight of hand, we need to look at the engine running this entire theory, the master unification equation.
The master unification equation is the covariant operator on this infinite lattice. It is a single, incredibly dense piece of mathematics that TDUFT claims dictates all physical interactions. To understand how the spin of these hyperons is decided, we have to look under the hood of this equation.
Let's walk through the mechanics of it. The first term is the derivative with respect to tau of d sub n.
Yes, d sub n is the dimensional node field at tier n. Simply put, this represents the foundational geometric nodes of the lattice itself, and the derivative tracks how this field changes or evolves dynamically over the lattice time parameter tau.
Okay, so that establishes the base grid. Next, we have b phi multiplied by v sub t. The source defines b phi as the antisymmetric golden ratio beta tensor and v sub t as the local torsion vector. How do those two things interact to align the spin of a particle?
This is where the geometry actually performs physical work. Imagine the lattice as a massive, rigid, three-dimensional grid of rubber bands. The torsion vector v sub t represents local twisting or stretching in that grid caused by the immense energy of the RHIC collision.
So the collision literally twists the architecture of space.
Yes, and the beta tensor b phi dictates the rules of that twist. Because it is an antisymmetric tensor based on the golden ratio, it forces the energy to resolve in a very specific geometric pattern. It's like twisting a wet towel. The tension forces the fabric to bunch up and align in parallel ridges.
Oh, I see.
When the lambda and anti-lambda particles condense out of that twisted lattice, their intrinsic spins are forced to align parallel to those geometric ridges.
That makes profound physical sense. The vacuum is literally acting as a mold, forcing the particles into an aligned state. But what about the final term in the equation? The one subtracting the natural log of phi multiplied by the gradient of s. The paper calls this the entropy current divergence.
If we connect this to the bigger picture, this final term is the exact mathematical origin of our 0.006 transaction fee. The gradient of S tracks how entropy, which in this context means the diffusion of state information, moves across the dimensional nodes of the lattice. When the particles are realized in the collision crossing the continuum limit, this entropy divergence term actively broadens the resonance state.
So it's actively smoothing out the sharp mathematical perfection of the lattice, leaving us with that residual entropy tax. That is a stunning piece of theoretical engineering. Dukas took a pre-existing equation, claimed it generates all mass spectra and vacuum densities, and applied its native mechanics to the RHIC data to get exactly 0.388.
It is undeniably elegant.
But I have to ask a crucial question about the scientific method here. A theory can sound beautiful, it can have all the right variables, but a valid scientific theory cannot just explain what we have already observed. It must successfully predict what will not happen. Does TDUFT pass a rigorous exclusivity check? Like, can it predict null results?
This is perhaps the most robust part of the paper. Because the RHIC scientists didn't just measure the lambda and anti-lambda pairs, In any good experiment, you have control groups. They looked at same sign pairs, meaning they measured the spin correlation between two lambda particles or between two anti-lambda particles. They also looked at entirely different families of particles like pairs of kaons.
And what did the physical data show for those control groups?
The physical measurements showed absolutely zero spin correlation. The spins were completely
A
random.
zero. Okay, so how does TDUFT explain why a lambda and an anti-lambda have a 0.388 correlation, but two lambdas have zero? If they're all being born from the same twisted lattice, should they all be aligned?
You would think so, but TDUFT explains the null result entirely through the geometry of the lattice itself. It comes back to that antisymmetric data tensor we discussed. According to the mechanics of the paper, generating an antimatter particle like the anti-lambda requires an inverse geometric orientation compared to regular matter.
So they're essentially mirrored projections on the grid.
Correct. But when the collider produces two particles of the same sign, two regular lambdas, they correspond to what TDUFT calls parallel tier crossings on the phi lattice. Because their geometric orientation is identical, they are crossing the parallel nodes in the exact same phase.
Let me see if I can visualize this. If the antisymmetric tensor is twisting the lattice in one direction, but you have two identical particles occupying parallel geometric tiers, do their interactions with the twist cancel out?
Mechanically, yes. It is constructive and destructive interference applied to vacuum geometry. The torsion vectors of the parallel tier crossings perfectly negate each other. The physical twist is effectively zeroed out for that specific pair. When the torsion cancels, the density operator in the master equation vanishes. The pure math literally outputs zero correlation for same sign pairs.
That is wild. It perfectly mirrors the experimental null result, not by tweaking a parameter, but by relying on the rigid rules of the geometry. But what about the kaon pairs and the computer simulations? The paper specifically calls out standard Monte Carlo event generators, like PyTHI.
PyTHI is the gold standard software tool in particle physics. It uses standard model parameters to simulate high-energy collisions. It essentially rolls complex weighted dice based on known probabilities to predict what will happen when particles smash together. But both the actual kaon physical measurements and the PyTHI computer simulations yielded a null result for this specific type of spin correlation.
Which means standard physics simulations fundamentally fail to anticipate this alignment.
Why? The explanation provided by TDUFT is devastatingly simple. PyTA fails to generate the 0.388 correlation because it lacks the foundational architecture of the reality it is trying to simulate. PyTHIA assumes a smooth, continuous, featureless vacuum. It does not possess a structured golden ratio grid in its programming.
So it's like trying to program a computer to play chess, but you tell a computer the board is just a smooth table. You can simulate sliding the pieces around all you want, but the fundamental rules of movement, the geometric law that dictates why a bishop can only move diagonally, literally do not exist in the simulation's environment. Without the checkered grid, the behavior of the pieces makes no sense. PyTHA doesn't have the geometric grid required to twist the particles into alignment.
That's a brilliant analogy. TDUFT demonstrates that the spin correlation is an exclusive signature of lattice geometry. It explains what correlates and mechanically why other pairings do not. But the theory undergoes one more critical stress test in this paper, and it concerns the behavior of these particles as they move through space.
Right, the separation problem. The RHIC data showed that this 0.388 correlation is highly localized. It is only strong at incredibly short ranges. When the lambda and anti-lambda particles are born, they possess tremendous kinetic energy. They fly apart rapidly. And the RHIC observed that as their rapidity separation increases, as they gain distance from one another, the spin correlation rapidly degrades and vanishes.
Standard physics often handles this degradation by applying an empirical decoherence length. They basically look at the data curve, see how fast the correlation drops off, and assign a mathematical parameter to match it. It's descriptive, but not necessarily mechanical.
Right.
TDUFT, however, models this fall-off dynamically using the master unification equation.
The paper provides the specific equation for this distance decay, c, as a function of delta, where delta is the separation distance equals 0.38 multiplied by e to the power of negative gamma phi times delta.
Which mathematically describes an exponential decay curve. But the mechanics behind that curve are what truly matter. Geometrically, this is not an arbitrary parameter.
So what is physically happening to the particles to make them lose their alignment?
Remember the entropy current divergence term, the one that generated our 0.006 transaction fee when the particles crossed the continuum limit.
Yes, the term that smooths out the lattice perfection.
That term doesn't just act once. As the particles physically separate and propagate across multiple geometric shells of the phi lattice, they are continuously subjected to that entropy divergence. Every time they cross a lattice node, the entropy current introduces a minute amount of state diffusion. The vacuum itself is actively working to erase their original psi-squared alignment.
Wait, so the vacuum is actively scrambling their connection the further they travel through it. It's like two devices connected to a Wi-Fi router. The router is the collision point, where the lattice geometry imparts the initial strong signal, the spin alignment. But as you carry those devices further away, moving through the walls and physical architecture of a building, the interference degrades the signal until it drops out completely.
Precisely. The geometric architecture of the vacuum, the structural walls of the lattice, acts as the source of interference. The rapid fall-off in correlation is a direct, unavoidable geometric consequence of propagating through a discretized space. It is not an ad hoc fix to make the graph look pretty.
So what does this all mean when we start zooming out? If this theoretical geometric vacuum dictates the exact numerical spin of hyperons at a microscopic level, if it cleanly explains why same-sign pairs don't correlate through parallel geometry, and if it perfectly models the mechanical decoherence of particles as they travel, what else is this lattice controlling? Because the paper makes it clear that this RHIC analysis is a subset of a much larger framework detailed in a 2025 work called Maximus Secrets of Reality.
The broader implications are staggering. The RHIC measurement is merely one projection of a fully unified theory. TDUFT claims that this infinite golden ratio for lattice is the foundation for virtually all fundamental phenomena in the universe.
To really grasp the scale of that claim, the source material explicitly references a historical macroscopic experiment from 1979, the Brillat-Hall experiment. Why does a paper about quantum hyperon spin care about an optical experiment from the 1970s?
Because the Brillat-Hall experiment was one of the most precise tests of the speed of light ever conducted. To understand its importance, we have to recognize that standard relativity and quantum chromodynamics rest on a foundational pillar called Lorentz invariance. This principle demands that the vacuum of space is perfectly isotropic.
Meaning the speed of light must be exactly identical in all directions, regardless of how the Earth is moving, rotating, or hurtling through the galaxy.
Exactly. Einstein's entire framework requires space to be featureless in this regard. But in 1979, Brillat and Hall used highly stabilized lasers to measure the speed of light in different orientations, and they did not find perfect isotropy. They measured a tiny persistent anisotropy, a variation in the speed of light depending on direction.
But the variation was incredibly small, right? The paper notes, it was at the level of 2 parts in 10 to the 15th power. That is a fraction with 14 zeros before the number.
It is an unimaginably small variation. For decades, many in the physics community have treated it as experimental noise or an instrumental artifact because standard physics insists the variation should be exactly 0.
But TDUFT claims it isn't noise.
No. TDUFT claims it is the macroscopic signature of the lattice. Because the vacuum is a structured geometric grid, it inherently possesses a grain much like a piece of wood. Light traveling with the grain moves differently than light traveling against it. The vacuum is naturally not isotropic, and the paper asserts that the exact same mathematical operators, the antisymmetric torsion and density operators that dictated the 0.388 spin correlation for hyperons, directly predict the specific non-zero anisotropy measured by Brillat and Hall.
Hold on. You were saying the same math that aligns quantum quarks also slows down lasers based on the geometric grain of the universe.
It goes even deeper than that. The paper claims that the universal harmonic series, the exact same attenuation math that generated our 0.006 entropy tax to bridge the gap between pure math and physical reality, is responsible for refining the speed of light itself.
How does a geometric math sequence dictate the speed limit of the universe?
TDUFT posits that the foundational ideal Trinitarian velocity on the pure virtual lattice is exactly 3 times 10 to the 8th meters per second, a clean, perfect integer. But when that theoretical velocity is projected into the physical continuum, it must pass through the infinite harmonic attenuation series.
Okay.
The physical environment dampens it, the geometry taxes it, and that mathematical sequence refines that perfect integer down to 2.9979 times 10 to the 8th meters per second, the precise messy speed of light we actually measure in a vacuum.
This is where I have to step in and play devil's advocate. Deriving the exact quantum spin of a hyperon, predicting the directional anisotropy of lasers, and deriving the exact decimal value of the speed of light, all from a single geometric framework based on the golden ratio. Is this truly the ultimate unified theory of everything? Or are we looking at the most sophisticated case of mathematical pareidolia in human history?
Pareidolia being the psychological tendency to see patterns where none exist, like faces in the clouds.
Exactly. I mean, if you give a brilliant mathematician an infinite harmonic series and a universal constant like the golden ratio, couldn't they theoretically twist and tweak the algebraic variables until it outputs whatever number they need? The math is beautiful, but how does the physics community actually test this? How do we prove it? It's predictive science, and not just an incredibly elegant mathematical illusion.
It is an essential skepticism, and the scientific method demands exactly that level of scrutiny. Dukas himself addresses the pathway for testability in the paper's conclusion. The key lies in the entropy tax, that 1.6% discrepancy governed by the entropy current divergence.
So we test the transaction fee.
Yes. The theoretical limit of this model is testable through future higher statistics measurements at the RHIC or the Large Hadron Collider. If experimentalists can measure the separation decoherence of these hyperons at vastly higher resolutions, and if the physical degradation of the spin perfectly matches the exponential decay curve predicted natively by the TDUFT entropy current divergence, that forces the physics community to pay attention. If the lattice mathematically predicts the exact curve of decoherence before the experiment is run, it graduates from mathematical curiosity to predictive physics.
It shifts the burden of proof. So we're left waiting for higher resolution data. But let's take a moment to look at the journey we've just been on. We started with a mystery number spat out by a particle collider, 0.388. A hard, undeniable measurement that the standard models of quantum chromodynamics simply could not predict without retroactively fitting their equations.
And we explored a framework, TDUFT, that naturally derives a baseline vacuum density of approximately 0.382 using pure golden ratio geometry, and perfectly bridges the gap to the physical 0.388 measurement through a rigorously defined transition mechanic, the entropy remainder.
The ultimate takeaway here for the listener is a fundamental shift in how we perceive reality. We have to rethink empty space. It is not a void. It is not a featureless stage where particles perform random acts. If Dukas is correct, the vacuum is an active structured architecture. It dictates the rules of the play. It aligns the quantum spins of hyperons, it enforces the speed limit of light, and it mathematically taxes particles with entropy as they drag themselves through its geometric grid.
It suggests an underlying harmony to the cosmos that is profoundly deterministic.
And that deterministic nature is exactly what I want to leave you, the listener, with today. A final thought to chew on as you look up at the night sky. If every physical constant, from the speed of light dictating relativity to the subatomic spin of quarks to the structural integrity of the atoms in your brain, is merely a different harmonic projection of a single geometric lattice built strictly on the golden ratio, what does that mean for the nature of existence? Does that mean the universe is less like a mechanical clockwork of interacting independent parts and more like a single, rigid, infinite fractal? And if everything around us and inside us is just pure geometry reading itself out mathematically into the physical world, where is the room for randomness or even free will in a perfectly tessellated cosmos?